Now the second part of the presentations, which is in this part of the presentations, I will show the electron pair distribution function technique and how it can be applied for characterizing amorphous and nanomaterials in a transmission electron microscope. Okay, so a crystalline material, a material in a solid form can either be well crystalline, or it can be a nanomaterial, or it could be an amorphous. Crystalline material shows sharp diffraction spots, or it can be seen, as you can see it in the left side of the slides, in a one-dimensional diffraction pattern. Once the particle size becomes smaller, the diffraction patterns becomes broader. And for an amorphous material, the diffraction patterns is very, very broad. So there is no direct way to extract any structural information for this type of material, for materials, I mean for the nanomaterials or from an amorphous material. Transmission electron microscopy or scanning tunneling microscopes can image single atoms or columns of an atom. It can also reconstruct atomic coordinates from three-dimensional tomographic reconstructions from different sections, but it is far from routine, and also many things needs to be sorted out, like you will have a beam damage if you have a delicate samples. The positional accuracy is much lower than any other crystallographic methods. One approach to solve this problem is to use pair distribution function to extract structural informations. In this method, high energy X-rays or neutrons or electrons are scattered off by a material and detected by a detector, very much like conventional powder diffraction experiment, which most of have you seen in a X-ray lab. The difference is that extremely shorter wavelengths are used and wide angular range data are collected. Results in a very wide range of reciprocal space can be proved. Before I explain what pair distribution functions or PDF means, let's first see one of the most important terminology which you will see in the PDF technique is Q or momentum transfer function. This simply can be derived by looking into the Bragg's law of diffraction. And incident beam K comes, and then it gets diffracted by the lattice plane, which is separated by interplanar distance of d. Then the Q or momentum transfer function simply derived from the incoming K int and the outgoing K final diffraction vector. So this Q you will encounter again and again in the different slides. So probably I will mention it again in some of my examples. What PDF means? First thing it may come to your mind, it's an acrobat reader used by almost everyone these days. But I'm not going to talk about this one here. I'm going to talk about a function known as pair distribution function. The PDF method is a total scattering technique for determination of local structures in nanostructures or amorphous material. The technique does not require periodicity, so it is well suitable for studying nanoscale features in a variety of materials. Pair distribution functions gives the probability of finding an atom at a distance r from a given atom. In the plot on the right, x-axis is the interatomic distance and y-axis is the probability. The process of obtaining PDF is, first one need to collect a diffraction data. It can be collected in a lab diffractometer or a synchrotron source. Each has its own advantages. If the data has been collected with a 2D detector, then one need to do azimuthal integration first to get a 1D profile, which is then transformed to get a structure factor function, and then at the end it is a Fourier transformation to get the PDF in the real space. More details of these different transformation steps I will explain you in next few slides. First step is to convert the, as I said before, first step is to convert the 2D data into 1D profile, and 1D profile intensity is plotted against Q, same Q as I mentioned before. And to do that, one need to do a background subtraction during this process. For example, in case the sample is collected using a capillary in a powder, it's a diffractometer, the diffraction contribution from a glass capillary needs to be subtracted. Now the obtained 1D profile intensity has all the coherent scattering which is coming from the materials or the structures of interest. Now the approach is the mathematically natural amplifications of the small signals in the data, especially in the high Q region of the scattering, as I have marked it with a different color. This is simply done by dividing the measured scattering intensity by the square of the atomic form factor, which is falling to a very small value at high Q range. As we all know, dividing a number by another small number results in a very large number, and weak signals at high Q, which is so difficult to get access, now amplified. And after that, another multiplications by Q that is also required. Now, as you can see, the abundance of a strong new signal, which I have marked it in the red, which is very apparent, which was very difficult to access in our original diffraction data. Now the experimental PDF denoted in the literatures as GR is the simple sine Fourier transformations of the total scattering structure factor functions, or FQ, which I have mentioned in the previous slides. Though the integration limit of the Fourier transformation is 0 to infinity, in practice Q mean and Q max is limited. So PDF is a truncated Fourier transformations of the scattering structure factor functions FQ. Usually Q max for synchrotron or for synchrotron data, one can get 30 to 50 inverse Armstrong. And let me show you the effect of a Fourier transformations. Where PDF for a nickel nanoparticle was simulated with different Qmax, first one with Qmax infinity and second with 15 inverse Armstrong. As you can see that there are different additional peaks which are marked with a pink color has been observed due to the limited Qmax. These additional peaks which does not belong to the structures come from the Fourier truncation effect. Though for extra synchrotron, obtained Qmax is much higher, but getting an access of the beamline is time consuming, and one need to apply for it first to get an access, which may approve or may not. So one can do a PDF obviously using a lab diffractometer, but the Qmax is much lower than synchrotron data, and one needs long experimental time. So then PDF, as I said, PDF can be extracted with X-ray. It can also be done by electron microscope. So PDF can also be obtained from electron diffraction data collected using a transmission electron microscope. The obtained PDF will be termed as ePDF or electron pair distribution functions in all my remaining slides. The process is the same as of the X-ray PDF. First, the electron diffraction data is collected in the TEM with a 2D detector, and then it is converted to 1D profile, and then it is transformed to structure functions, and which is then converted to ePDF by Fourier transformation. Exactly the same way. The difference between X-ray and electron diffractions, I need to remind you again, the wavelength is very small in comparison to X-ray, and also the theta value for the diffractions is very small due to the Bragg's law. So in this case, momentum transfer functions, or Q, which I mentioned before, needs to be modified. So now Q is 2 pi by d. And also other important thing is the electron scattering factor drop much faster than the X-ray. So in most of the cases, using electron diffractions, one can get a Qmax 10 to 23 Armstrong quite routinely. So TM is ideal for calculating pair distribution function. Now, how close are the results obtained from two different sources, XPDF and ePDF? For this, we have taken a recent example where gold nanoparticles was deposited on holy carbon grid, and 2D electron diffraction pattern was collected. From the same gold nanoparticle, a powder diffraction data was collected in the beamline, and the collected from these two diffraction data, from electron diffractions and X-ray diffraction, ePDF and XPDF was calculated, and then the PDF was fitted with the bulk gold nanostructures. From the obtained result, you can see it is possible to do a model fitting with the electron diffraction PDF, and also the PDF obtained by these two methods are comparable. So that means you can also use PDF routinely using your electron microscope. So the major advantage of using ePDF is that data acquisition time is much short than doing it in a lab diffractometer, and also it's a very small beam size. With a very small beam size in a TEM, you can observe local structural changes. And most importantly, most research centers have an access to a TEM so that you can do PDF in your own premises whenever you want with your material. And all the mathematical process which I have mentioned in my last couple of slides of calculating 1D profile to ePDF from a two-dimensional data can be done using a dedicated software which we call ePDF suite provided by Nanomegas. Next, now I'll show you a few examples. Here I'm showing an example of two types of materials. One is an amorphous material and another one is a nanomaterial, where data was collected in an image plate and using a CCD detector respectively. Subsequently, it was converted to ePDF using ePDF suite software. From the calculated PDF, you can see for the amorphous material there is no peak after 7 Armstrong, and for the nanomaterials there is a peak in the entire R value as expected. Now the second example. Is studying local structures in amorphous material using ePDF. First 2D diffraction data was collected from an opal sample. Opal is a mixture of two forms of silicon oxide. The ePDF was calculated from the diffraction pattern using ePDF suite software. And from the obtained PDF result, you can see two things. First thing is you can see a short range order, and then you can also see the interatomic distances matches belongs to the silicon oxide or oxygen distances matches with the tridymite, cristobalite forms of silicon oxide. Third example is a phase identifications for nanomaterial using ePDF, where 2D electron diffraction data was collected from these nanoparticles and then it was converted to ePDF. For sodium yttrium fluorides, actually there are two different phases. One is a cubic phase and the other one is an hexagonal phase. For both phases, theoretical PDF was calculated and it was compared with the experimental PDF by Pearson correlations. And we have seen the Pearson correlations for the hexagonal phase is much higher than the cubic phase. And this result was also been confirmed independently by A-star phase mapping in TEM. Then, one of the most important points, as we all know, the integrated intensity of the PDF peaks represents the coordination number. In the first part of my presentations, I have shown that electron diffraction data is dynamical. Then what is the effect of dynamical scattering on the calculated ePDF? The effect was demonstrated by calculating ePDF with different mean free path of elastic scattering for a face-centered cubic lattice, and it was shown that for multiple scattering, multiple scattering does not influence the peak positions, though it affects the height of the peaks. I have already shown you the precession helps to reduce dynamical scattering. That means if we want to calculate coordination number or want to do any quantitative modeling, it is advisable to do beam precessions. From our experiments in all these years, we have seen precession really helps to get better kinematical data for nanoparticles for ePDF calculations, which I will show in the next slides. Here diffraction data from nanoparticles was collected with and without beam precession at two different temperatures, and room temperature and liquid nitrogen temperatures, and we have seen the ePDF data obtained with beam precessions and collected at low temperatures give the best fitting during the structural modeling. And also the calculated coordination number from the precession ePDF data matches most closely with the theoretical coordination number for a gold nanoparticle. This result we have published last year in JPCC, and it was highlighted in the cover page of the journal. If you see the publications, you will see the more details of collecting and processing the data. The last example is from Aerosil, where diffraction data was collected using direct electron detection camera, and the obtained ePDF was compared with the XPDF results using from a synchrotron data sets, and it is comparable. So let me stress again that the results obtained from ePDF from electron diffraction from electron microscope is comparable with the synchrotron data, but as you have a TEM in your institute or in your lab, you can use it routinely for your experiments to analyze amorphous or nanomaterials. And this is a new development which we are currently working with Professor Simon Billing from Columbia University, New York, where instead of doing point analysis, first we collect data from an area with spatial resolutions of 10 nanometer. Then in the second step, ePDF is calculated automatically from each of these positions, and the obtained results can be used to observe small structural changes in different locations, or to do a phase map in case there are more than one amorphous phase present in your material. This is a new development, so I will show very brief. So as you can see in the left of the present image, that there is a virtual bright field image from where data was collected. Some part is crystalline, some part is amorphous. Then electron PDF was calculated from thousands of diffraction patterns automatically, and we have observed some structural variations, especially to the interface, where from two interface between the two amorphous phases, and also the interface between crystalline and amorphous. And you will be able to see more details on this analysis in our future publications. And several other parameters like peak width, peak height, you can also plot it in two-dimensional image to observe many other structural changes. So this is a new development from our end in terms of ePDF mapping. To summarize, ePDF provides many informations: the length of the ordering, it does materials identifications, and using ePDF mapping, you can observe variations in the amorphous structural changes in amorphous materials, or if you want to see any in situ process in an amorphous material. So that's end of my presentation. So personally, for me, it is a very challenging and rewarding journey to study different types of materials using electron diffraction techniques, and to develop new methods for structural characterizations. I'm sure you will try electron diffractions, 3D electron diffractions, or pair distribution functions after these presentations. And thanks everyone for joining this webinar. Now I'll pass to Dr. Ghoshal, who will show some more exciting results from his work. Thank you everyone for your attention.